Now let me see. Alright, let me see if I can open this chat. Far better than most peeps to do assume. I don't think it's the connection. I think it's primarily the microphone that I have. I have a dedicated microphone, so that's why you don't hear all the static. It's a condensed microphone, but I mean it could be anything. How do I get rid of this? I'll put this down here, and I'm gonna put this on the side. All right, can you guys see my screen? And I'm gonna try to take as little time as possible so that if there are more things that we need to talk about, I can spend time talking about that. I don't know what that line in the middle is. Whoa. Okay, never mind. All right, so thank you for joining the numerical methods review. I'm gonna be doing a quick review for exam 1. And I'm going to try to talk about all the different topics, and I'm going to try primarily, so the way that I'm going to do this is I'm going to give kind of like a crash course on this, so we only take like half an hour to an hour. So those of you who are just curious of, oh, what do I need to know for the exam, or how do I prepare for the exam, or do I know exactly what I need for the exam, you can kind of like get out of the way. And then for those of you who are lost or haven't had a chance to study or don't really understand the concept, I have my book and I can go over the different concepts and the methods and how to tackle them. So I can even go deeper into the derivation and explain how some of these things came to be. But at first I want to just kind of like go a rundown of everything that you need to know, so that those of you who are just here again just for double check or just want to know the bare minimum so you can pass the exam, then you can kind of like leave and go on with your day. So the main thing that I want to talk about, so what are numerical methods? And I'm not going to give you the full lecture because you guys are already in the class. You go to lecture, so you must know what we talk about or what I refer to when I say errors or real numbers or all the different vocabulary. But when we talk about numerical methods, it's the whole idea. So the whole idea of numerical methods is you have two ways of finding things. You have the first one, and this is not necessarily on the exam, but this is so you get a better idea. Everything that you have learned up to this point, has what is known as an analytical solution. So an analytical solution is, for example, if I give you a function f of x that is dot dot dot, that is something. I'm sorry, not the f prime. If I give you a function, if you were to use chain rule or any form of approximation of that tangent line, at that point you should be able to find the f prime. You should be able to find the first derivative. So if I gave you something like 2x to the fourth and I want you to find the first derivative, this will be ax. But why? Because of the process of the chain rule. So this is what is known as an analytical solution. However, this is very minimal. This is very like contained, kind of like a term that in physics they will say it's a vacuum. Not all systems in real life behave this way. Not all equations in real life are easy and are easy to manage and move around and everything, which is the reason why we have so many methods for root seeking, to finding solution, that you hear Dr. Kasap in the class talking about, okay, today we're going to introduce Newton-Raphson. Today we're going to talk about Secant Method, or we're going to talk about bisection. Like those three methods, which I'm going to get there in probably in about 15 minutes. Those three methods talk about the same thing. It's all about finding the x value such that f of x equals to 0, which this is something from basic intermediate of college algebra. What x value makes my function equal to 0? And the reason we use those routines is because not all the problems that we want to solve have an easy form, has something that is very easy to explain. Like if you try to do chain rule or anything by hand of like the in project 2, the friction factor, every time you try to solve those type of problems, they just get more and more complicated. And then that's why we need to implement computers, because there are ways of solving, there are ways of going about these solutions, about doing root seeking and optimization and all of that, that we implement numerical methods. So there are two ways of finding solution. We have the analytical solution, which I already talked about, and then we have what is known as the numerical solution. So the numerical solution, both of them, they accomplish the same thing. We want to find a specific condition. We want to find like, oh, give me x if f of x is equal to 0. There are two ways that we can find this. We can find it using an analytical solution like you did in Calc 1 or in single variable calculus, or you can find a numerical solution, which is what this whole class is about. Now, numerical solutions, one thing that you have to always keep in mind is they are an approximation. So whereas an analytical solution, and this is very good that you know it for the second exam, the analytical solution, it's, whoops, I think I erased most that I needed. There you go. The analytical solution, it's what is known as an exact solution. So this one is an exact. And the numerical solution is an approximation. However, because we have gotten so good at these numerical routines, what the methods that we use, you will notice that they're extremely close to the analytical solution, which is why in your projects, in your codes, we often have like, oh, this is the result. Like if you remember from project 1, this is the evaluation of the first derivative using forward difference. This one is the one using backward difference. This one is the one using central difference, and central difference was the most accurate because of course it had more data points. And then we compare it with the exact solution, with the exact solution of the first derivative, which is we did the chain rule and then we evaluated at that point. And you saw that the values are extremely close, very close, and there is an error, and there is a bunch of problems that come after from that, and I'll elaborate on that in a second. But one thing that as an engineers and scientists we have come to understand is that our numerical approximations, while they're not exact, they're approximations, they're extremely close to the real value so that we can use them, we can implement them, and we can make assumptions based on those values. So why anybody will have a very difficult time understanding how, for example, how the heat transfer on a fan, like if we're trying to do an aerospace engine, or if we want to do a gas turbine for Siemens, if we have a fan that transfers heat, that's the main purpose of a fan. Like if I have a triangular fin like this, or let me do something like this. Like if I have a bar like this, and this bar transfers heat from the base, there is a temperature at the base and there is a temperature at the end node at the end. What we can do with numerical approximations, and this is a very rough example, is that we can create nodes that are separated by a certain distance. They're separated by a certain delta, and all of these nodes, they have a value. They each have a value, or they each have a pertaining number that pertains to the index. And what happens is, if I do my numerical solution, what I can do is treat this system as a discrete system. So instead of coming up with a solution, instead of coming up with an equation that tells me how the heat transfer is happening in this bar, like if I want to come up with an explanation of something that says, oh yeah, the heat transfer is gonna happen like this. Like imagine this is time, this is temperature, it's something like this. Like this one is your function with respect to time of the temperature. It's like, whoa, okay. But the reality is this is extremely simplified. Like for me to come up with a relationship like this, there's so many assumptions that I have to make. There's so many things that I have to kind of like omit in my formulation that it makes no sense. It's not really accurate. It might be good for a study for me to get an idea of how my system is behaving, how my system is changing, but it doesn't give me anything, any meaningful information for me as an engineer to take decisions on how I'm gonna go about manufacturing this thing. What needs to be the length? What are the dimensions? What needs to be the material? Is the heat too much? What are the temperatures that I can achieve? So this one pretty much is A heat transfer problem is what you can consider as a partial differential equation, which is where in PDEs, that's where numerical solutions like they shine, because PDEs are extremely complicated to solve, and if we make certain assumptions, we can actually treat it as either an ordinary differential equation, or we can solve the PDE by using numerical solutions. So in this case, if I were to take all of those points, like if I have reading of all of those points or measure them, I can go about solving this project using a finite difference approximation. And what I can obtain from this is I can obtain a vector, at least for the purposes of this class. If you go more advanced into heat transfer, you can obtain more things, but for the purposes of this class, if I treat this as a discrete value, I can come up with a vector, because this is a system of equation. I can come up with a vector that will tell me my temperature at 1, temperature at 3, temperature at 4, and so forth, depending on how many nodes I have. So now in this, if I solve this problem as a numerical methods problem, at the end I will have the solution for the temperature at each of the nodes. And if these nodes are very close, that means if my delta is sufficiently small, then all of these nodes will be so close together that I can get a smooth graph that tells me how the temperature is changing across the beam, which is exactly what I would like to do as far as numerical methods go. So they're good and bad when it comes to numerical methods. Their approximation, it simplifies a problem like this, where we don't have a way of describing perhaps without making extreme assumptions. And it's also very good because we can find solutions that are very accurate, very close to the exact solution, and we can benefit from using computer, because that's the second part that I want to talk about. So what happens with numerical solutions different than analytical solution, they're a repeated process. So what I mean by a repeated process is that what I'm sure of you looking at how to solve bisection, how to solve Newton-Raphson, how to do traditional root seeking, is that what you've noticed is that it's the repetition of the same process. It's like, for example, if I'm doing Newton-Raphson, my new solution, it's equal to, or let me put here, let me use the same notation that you guys use in class, or that the book uses. It's equal to my previous solution minus my function evaluated by the first derivative of that function at that current root. So in what is going to happen is, if this one is my x1, so if I'm trying to find my first solution, I'm going to use my initial guess. I'm going to evaluate my function that is given at the initial guess, and then the first derivative at the initial guess. And then I'm going to take this value, and to find the second approximation of my root, again, this is all the same root. I'm just finding a better approximation. Give me 1 second, Matthew. And if I put this in here, and I do the same thing, I evaluate my function at that point, every single time that I'm doing something, I keep using my previous iteration. So that's why it's called a repeated process, or a root seeking process, because I'm using my previous solution, my previous iteration, to better understand or to better approximate the final solution. There is a real solution, and every single time that I do, that's why it's called an iteration. An iteration is when you do something multiple times, like kind of like what iPhone is doing with their shitty iPhones. They come up with the iPhone 1, then 2, then 3, then 4, then 5. Those are known as iterations. That's the same idea that we're doing here. We come up with a solution, and we feed that solution into our equation again to find a better approximation of a solution, and that one we call it our second iteration. And then if we go into our third iteration, fourth iteration, fifth iteration, we keep using our values from before. Now, Matthew, do you have a question? Do you have a microphone, or do you need me to open the chat?
Yeah,
Okay.
I'm good. So I was just wondering, I think someone asked in lecture before if we're given the initial guesses, and I think you said no. Is that right?
No, you're always given the initial guess. You have to always be given the initial guess, at least for the
Oh,
purpose of
okay.
this class. Yeah, if you're doing Newton-Raphson, so if you're doing bisection, you will be given the bracket. You will be given your A and your B. If you're doing repeated process, what is 2.1? Yeah, it says repeated process. So sorry for the curvy, the handwriting. But if in Newton-Raphson, we will provide you. So Newton-Raphson, just to kind of like shift to the side. For Newton-Raphson, we will provide you the function, and we will provide you your initial guess. What we will not provide you that you need to find is the f prime. So if we give you a function, make sure you know how to take the first derivative of things, because you're gonna need it for the Newton-Raphson root-seeking method. But we will provide you with an f prime, and we will give you the function, and we will give you the x naught. So those two things are going to be provided for you, and the only thing you really need to find that is a requirement of Newton-Raphson is to find the f prime. For bisection, we will give you the function, and we will give you your a and b bracket, so you know the bracket that you're required to use. But yeah, so that's kind of like the idea. Hopefully that answered the question, but that's the idea. What?
Yeah, that answered. Thank you.
Okay, perfect. Thank you.
Quick question. Will we be given like the number of iterations we need to solve for, or is it kind of just
No,
get as close
that
as
will you
possible?
will not be. Let me see. Let me think. I believe questions are gonna be more specific in the sense of like, after your third iteration, what is your approximated solution? What is your residual at that approximated solution, and what if your iterative convergence at that approximated solution? So they will not tell you when to stop, but they will specify like, oh, at that iteration, can you tell me these values? Can you tell me these details? And then they can then tell you something like, oh, can you do it at the second iteration? I think I wrote this backward. Can you do it at the second iteration or something like that? And the same idea. So,
Okay,
mhm.
that makes sense.
What is your question? Let me open this so I can have it here. Question: for bisection, are we given the tolerance? No, you don't need the tolerance for as far as code. There's gonna be a question that has to do with tolerance, but you will not be given a tolerance. There is a way for you to calculate a tolerance depending on the number of iterations. That can be a question on the exam, but you will not be given like a tolerance, because the whole idea that we use tolerance is a stopping point for our code. It's kind of like, oh, we have achieved a good enough solution, let's stop, because your code will never stop. These numerical solutions are, yeah, exactly. You have a formula for that, so make sure you understand it. But numerical methods, numerical solutions are an infinite process. They never stop unless you specify a tolerance. How far down the rabbit hole do you want to go, which is either by the residual or by the iterative convergence. Ideally, you will implement both of them, but those are your stopping criteria, which you have implemented when you're working on the code. So you're not going to be given the tolerances. However, there is a question in which you have to find it, and tolerances are primarily for being used in the code, in writing our routines. So I am going to move on, and I'm going to start talking about the kind of like what's prevalent for the exam, so you know it. Let's see. So for the exam, as far as the purposes of the exam go, you have to understand the idea of the main sources of errors. And this isn't something that you guys already talk about in class. So the main sources of error, there are two main sources of error. The first one is what is known as the round of error. And the second one that we see, these are the two main sources of error for all computational methods, like for numerical methods. So round off, and there is what is known as truncation. So there's round off error and truncation error. Those are the main forms of error. And now, if you want a little bit more detail about this, I'm gonna go over the exam again, as I mentioned before. So, because I feel like I already went on a tangent talking about numerical methods. So for main source of error, you just have to know that round off error and truncation error, those are your two main forms of error. You have to know how to, so let me just put a star here next to it. You have to know how to go from real numbers into binary. Now, it's very important that you pay attention to directions, because at the like the first slide or the first section of your exam is going to tell you how many significant figures you have to use for all calculations in order for to have the same, like, similar results to us. So if you're the kind of person that says, oh, 1.24 and there is more stuff, but you say, nah, I'm just going to keep this and use it on my next operation, we're going to have different answers. If I remember correctly, you have to go all the way to like the five decimal places after the decimal. So you have to, all calculations that you do, you have to do them with 5 decimal places. And at the end, for the purpose of the solution, all solutions, if I remember correctly, make sure you read the first paragraph on your exam. They're all gonna be chopped at the second decimal place. So in this case, this will become 1.24. Do not round. Does that say into? Oh, I'm sorry, that says binary. Let me see if I can write this. That probably looks better. But yeah, that says binary. So how to go from binary, my mind. So yeah, when you're reporting your solution, you have to make sure you chop. You do not round. Even if this is a 5 and you were taught that this will become a 1.25 or something like that. No, if it says you should chop at the second decimal place, you're pretty much just dropping everything else. It's kind of like you're omitting extra information. So do keep that in mind. And when you're practicing when you're working on this, on going from real numbers into imaginary, try something difficult. Try something like 32.5 into binary. And the reason for this is because when you take a decimal value, if you take an integer into binary, you're gonna get an exact value. If you take a decimal into binary, you're gonna have something like, let me see, you're gonna have something like 1. I love how I'm putting a 2 in there. You could have something like this: 1 0 1 0, and then a dot, and then your decimal part will be like a repetition of things. You're gonna have a value, but then at some point it starts repeating. So the way that you're gonna report that will be something like this, which means that this repeats over and over and over. I'm sure some of you are familiar with this, but that's why it's very important that you familiarize yourself with going from make sure you do difficult values. I believe you're allowed to use a calculator in this case. So if you have something like a TI 36X Pro or any calculator of that matter, this is usually we have exams on the EPC. This semester we're not having them on the EPC, so you're taking it from home. So we cannot prevent you from using technology or anything like that. But if you have a calculator, you can plug this into the calculator and do it like that. It's up to you. But ideally, make sure you know how to do binary to decimal and decimal to binary. If you do it on a calculator like that, if you happen to be one of the persons that has a TI 30X, just drop out. That's a shitty calculator. Please don't have that. Have something that is at least half decent. But yeah, this is something that you can do. You can do or you can do it on paper. You can do it on the calculator or anything like that. But make sure you know this for the exam. I'm not your parents. I'm not gonna be looking at you and see what you're doing. You're more than welcome to do whatever you want, as long as it's within the lockdown browser and you're respecting the UCF code on content. Food is done. I hear the microwave. Yeah, somebody heard the microwave. Okay, so give me 1 second. Let's see. So the next thing will be storing. So if you want to, another thing that you have to know, so know how to go from real numbers into binary and how to go the other way around. You also have to know how to store real values in binary, like how the computer stores the real values into the binary. And I'm trying to remember what I mean by this. You have to understand the conceptual idea of how they are stored, it's kind of like what I was talking about before, how the system will only store a certain number of binary. Let me see, storing real values. What did I mean by that? I think that's what I was talking about, how the finite memory on the computer, if I want to store something like, what kind of error do I have? So let me give you an example. Like how float is something, is that like bits or bytes for what? For the binary? how it flows. So what I was trying to say is, for me, going from a real value, going from something like 32.5, if I want to make it into a binary number and I want to store it in my computer, it's what I told you before. Like if you have 101.100101, and this goes on forever, when the computer wants to store it in the memory, it will chop it at a certain point. Like there is only so much of this that it will store. So in this case, this will not be round of error. This will be a form of truncation error, if I remember correctly. This will induce truncation error because we're truncating an infinite process. However, we're not doing any sort of rounding. So for the computer to store a decimal value, because an integer to binary, it's not all questions are multiple choice. It's a mix between multiple choice and single choice questions. So some of the conceptual questions will only have one solution, whereas some of the conceptual questions will have multiple solutions. And then moving on from there, once you go into the actual workout problems, those will also have a different value, different number of solutions. So keep that in mind. If you big oof. Is it all conceptual? No. The way that the exam is going to go is you're going to have a mix of conceptuals and non-conceptual questions. Like some of the problems are very, very quick workout problems, like, oh, go from 32.5 into binary. Like that could be an example of a quick question. And some of them will be something like, hey, what are the main sources of error in all numerical computation? Like very easy questions that you can just answer. That they only have one or two solutions, or you can just pick the correct solution. Those are for like the first 10 or 15 questions, and then the last, I believe, is the first 15 questions, because it's 25 questions in total, and something like that. And then the last 10 questions are divided equally. 5 are all about Newton-Raphson, like how making Newton-Raphson by hand, like doing the process by hand. And the next 5 questions are about bisection. So bisection and Newton-Raphson, that's something that I believe I stress during my teaching in the lab, that make sure even though we're not covering bisection in the code, make sure you know how to do it by hand, because that's most likely what's going to be on the exam. So you're going to have Newton-Raphson and you're going to have bisection. Those are going to be the big workout problem, which we're going to give you a function, we're going to give you your initial conditions and like the stuff that you need, and we're going to ask you, how do you set up the equation? What are the iterative, the residual at this solution, the initial solution or whatever solution at a certain iteration? What is the iterative convergence? How do you guarantee that this is going to converge based on Newton-Raphson? But in this question, they only ask about final result now. No. They can ask you for a result at any iteration. So if you're doing Newton-Raphson and you're at the second iteration, like if you're at your second, let me see. So if you're at your second iteration, I can ask you, hey, calculate the residual at that second iteration, calculate the epsilon or the iterative convergence at that second iteration, or calculate something else. But in this question, they also like the answer sheet quizzes. Exactly. Yeah, it's a similar idea. So when you're doing this process, when you're going on about this process, when you do it by hand, it's the exact same thing the computer is doing. Like the computer, every time it's showing you, when you do the code, and every time it's showing you like, oh, this is the first iteration, second iteration, third iteration, it's the same thing that you will be doing by hand. Like if you have worked any of the problems from Newton-Raphson or bisection, you will notice that the same exact thing that you are doing by hand. Like if you look at your code, go back and look at your code, it's the exact same thing that the code is doing. The only difference is there is a bunch of for loops involved and computer logic. But in reality, if you boiled everything down, the computer is just doing the exact same thing we want you to do by hand. The difference is the computer is not going to fuck it up. You will. So that's why we use computers for when it comes to this sort of situations. No problem. All right. So I'm going to move on. You have to know real numbering to binary, know the benefits or like the bad things. Know the bad things about it. So for example, if we take a real number, we make it a binary, a real number will have a decimal. The decimal will translate in binary as an infinite repeating sequence of a particular combination like 0, 1, 0 or something like that. And so we are incurring truncation error when we store or real values as binary numbers. So make sure you know that. Then another thing that I want to talk about is how do we represent 0? So how to represent. So how do we represent 0 in real? Which means in floating numbers. So if I want to represent 0, and this is something that I kind of like showed during my lab session, is we have two options. So there are two ways of representing in 0. 0 cannot be stored exactly. It cannot be represented exactly in the computer memory. It has to be approximated. And there are two ways of doing this. We have, depending on what you're working on, you have single precision and you have double precision. So for single precision, both of these guys are gonna be arranged. We have, oh, that's disgusting. Let me see if I can make this fancy. Give me 1 second. There you go. And I want to write it up here. I'm gonna get my handy dandy ruler. Ah shit, I'm in the eraser. There you go. There you go. And I'm gonna move this guy down right here. And there we go. And there we go. All right, now I can get rid of the ruler. So my range is gonna be something like this. Let me see. So the way we represent values in single precision, assume that 0 is here in the middle. If I want to represent my positive values in single precision, I'm gonna have 10 to the negative 38 to 10 to the 38. And that's on the right side of 0. And on the left side of 0, I'm gonna have negative 10 to negative 38 and negative 10 to 38. And then for double precision, I'm gonna have 10 to the negative 308 and 10 to 308. And then over here, I'm gonna have negative 10 to negative 308 and negative 10 to 308. So how do I represent 0? I represent it as an approximation. It's any value between these two for single precision, or between these two. So if somebody were to ask you, like if somebody was pointing a gun at your face and they were like, hey, numerical methods is my shit, it gets me hard. How do I represent single precision? How do I represent 0 in single precision? You can either say, you can represent it as 10 to the 38, or you can represent it as negative 10 to the negative 38. Like in any one of these two will be correct. And then in double, you can represent it as 10 to the negative, I better die. You can represent it as 10 to the negative 308, or you can represent it as negative 10 to the 308. These both are very close. So you can think of it, I choose that. Hey, don't kink shame me. You can think of this as a limit. You're approaching 0 from the left, or you're approaching 0 for the right. For the purposes of the exam, if I ask you, how do you represent 0 in real as a single precision, you will be given one of these two options. You either will be given this one, or you will be given this one. You are not going to be given both of them because it's redundant, it's confusing, it's stupid. So you're only going to be given one of them. However, make sure you know that there are two possibilities. You can represent single precision like this, or you can represent 0 in single precision like that, or you can represent 0 in double precision like this, either negative 10 to the negative 308 or 10 to the negative 308. This is something that you want to make sure you know. Now, in the same way, how do you express a big value? So these are the ranges of the values that we can write. So what is, in single precision, what is the maximum positive value for real that I can write? It will be this one. This will be the max, or if you want to call it the largest. And then in double precision, it will be this one. I feel like my English starts getting bad after talking for so much. Plus, his food. So yeah, this will be the max number that you can write, and this over here will be the. I don't want to call it minimum, but I want to call it like the maximum negative number. So it's again, it's redundant. They're probably gonna ask you something about the maximum number on the positive side. Very unlikely that they will ask anything on the negative side because it's the same thing. You're just changing the sign. So. After I fucked up the question because I'm not a computer, hell will go buy 32 watermelons at the Lucas Colleges. Any other math problem example person will. If I was in a room with you, Hitler, I'll turn on myself. Okay. But yeah, so make sure you know that. Make sure you understand this and how to represent zero in both single and double precision for real values, and how to represent what is the largest value that you can write in both single and double precision. Now, let's see. I'm a little sick. So the next thing that I want to talk about machine precision. So machine precision. Let me see if I can write this correctly. Precision. There we go. Perfecto. So machine precision. The idea of machine precision is this is the on the twice Corona. I'm gonna start coughing. The main idea of machine precision is, and I'm just gonna give you the definition so you have it and you know exactly what the solution is. It's the smallest, and I'm gonna write all in cursive because that's the way I am. Is the smallest value you can add or subtract. So this is all you need to know. So it's the smallest value that you can add or subtract from, I don't remember if it's from 1 and it still be able to tell a difference. It's something like that. But I know it's the smallest value that you can add or subtract. Every semester I have people come up to me and they're like, oh, it's just the smallest value that you can add. Or other people say it's just the smallest value that you can subtract. And I'm always looking at them and I'm like, okay, listen here, you piece of shit. Because you're probably using it like a last semester exam or something like that. It's the smallest value that you can add or subtract. It's both of them. And it's not only one of them. It's both of them. So if you're one of those retards who are studying from a last semester exam or like a previous year exam, something like 2015, 2004 or anything like that, the asshole who wrote the solutions to those exams, he wrote them wrong or she wrote them wrong. It's like a stupid Surface Pro or something like that. So you have to be careful. If you happen to have something like that, I don't have a problem with any of that. I think you should use your resources if you happen to be lucky enough to have it, or if you had to, I don't know, give head to someone for you to be able to obtain them. That's your business. That's not something that I care for. But it's very important that you understand that you have to be careful. Those solutions are not correct. Some of those solutions are correct. Most of them are not. So if you have a question with something like that, you have to bring it. That's something that I don't know. That's up to you. But that's something that you have to keep in mind, because don't. If you see something in lecture, if we cover something during the lab or anything like that, you have to be very careful, because if you have to not just fully believe it and like fight it or anything like that. Like have some believe in yourself a little bit. And if you think something is a particular way, even if a solution from like this random guy that graduated in 2004 and is now working for whoever, you don't know the validity of that. Like when I go back to my codes, when I took this course, like when I go back to my code that I wrote for this class, like I share with like all my friends and everything. Yeah, I'm recording. The review should not last. I solely work it. Yeah, I'm recording it right now, so I'll upload it. And if you send me a message, I'll send you like an unpublished YouTube link or something. I'll probably put it on YouTube and then let you guys share the link among yourself. But when I go back and I look at my code, like I look at it, I think it's disgusting, because there are so many things that I've learned from that point on that I had no idea what I was doing. And that's very important, because nobody goes back to old code. Like I don't go back and change those codes. I don't call my friend who they all already graduated. Everybody graduated, but like I didn't call my friends the next semester and it's like, hey, you remember the Newton-Raphson code? Yeah, I fucked up. There's something that you need to change. No, it's like everything just was sent like that and I move on. So be very careful when you're using previous semester resources. Don't just believe it without any sort of like doubt. That's really bad. I make my face smell like people at Robert Twister account getting no corona from the headset. So yeah, so this is the smallest value that you can add or subtract. I believe it's from 1 and still be able to tell the difference. That's pretty much what machine precision is. Now this whole machine precision business is something that you saw in your first project. In your first project when we were talking about finite difference. And this I want to go back to this. I'm gonna go on a little bit of a tangent. And I want you to understand. This is something that I might revisit later, but I just want to go over it real quick. So the reason machine precision happens, to tell the difference between that. Between what? Between adding or subtracting. So it's the smallest value that you can add or subtract from what and still be able to tell the difference. And this, that's why I want to talk about project 1. So in project 1, you were given a graph that was a function of delta and a function of the error, the absolute value of the error. And one thing that you notice is as you went to the right, delta, which is your step size, it becomes small. And this is your error. As you go up, it increases. And what we were seeing in that graph is that when we were using something like central finite difference, forward finite difference, or whatever, we noticed that the error was going down until a certain value. There was a certain particular value for delta, which after that point, our error started creeping back up, and we started to incur what is known as run of error in our code. Why did this happen? Like why is that something that happened? Why is that something that affected our code? Because of machine precision, of machine epsilon. If I'm doing something like forward or finite difference, if I'm approximating, let's say I want to approximate my first derivative at a certain point, and I'm gonna use finite difference. So I'm gonna say, okay, so f x at that point plus my delta minus f at that point over my delta over my step size. This is the approximation of the first derivative. If I know my function, if I'm given my function and I know the x value, and I can implement a step size. And this is something that you have to know. You have to know finite difference, and I will show you in a second what we're expecting from you on the exam. But this is something that you have to understand, that if I decrease this delta, if I decrease it, my approximation will be better. Like my approximation will be more accurate, because if you think about it, the whole idea of doing, like, finding, if I'm given a function like that and I want to approximate the first derivative at this point, this is what is known as a secant line. Like a tangent line. A tangent line is a line that I draw over a curve, like adjacent or touching the curve. And this should only touch it once. However, when I'm doing numerical methods, when I'm doing something like forward finite difference, central finite difference, or backward finite difference, I need 2 points. I have to pick a point, which is the one that I'm interested in evaluating, and then I have to pick a second point, which is that point plus a delta. And I'm getting that my internet connection is unstable. Can you guys still hear me? I think the neighbors are starting to watch the 4K midget porn. So, well, I mean, it's recorded, so I'll just keep talking. If you guys cannot hear me, just let me know. Okay, perfect. Just deduce them back. So the whole idea is I'm starting with a secant line. I'm starting with something like this. However, I want it to be a tangent line at what point? Because that's the definition of the first derivative. It's a tangent at a point. So what I'm going to do is this distance between those 2 points, which is my x, I need to bring it down. I need to make it smaller and smaller, so that this point right here, it will slowly creep this direction. Like, it will slowly go towards this side until at a certain point they're so close together that I obtain what is my tangent line. which is exactly what I want. So I'm going from having something like a secant line, depending of the distance between this delta, to having a tangent line. Now there is nobody in numerical methods, nobody in like industry or anything like that can tell you what this value should be, the delta value. Why? Because as you saw from project 1, me decreasing the delta, me decreasing the distance between these values, between these two x's, is good. That's very good because it gives me a more accurate solution for my first derivative. I get my I have my first derivative. The smaller my delta is, the better my approximation. However, at some point I can make it so small, like if I just go ape shit, if I just go bananas and I'm like, fuck it, I have a whatever 128 gigabytes of memory. I don't even have to download 4K porn. I can make 4K porn using machine learning and deepfake and everything. If you go too small on this delta, what happens is that you reach that point of machine epsilon, because the computer achieve machine precision, which is, it's funny enough, for double precision, it's like 10 to the negative 15, 10 to the negative 16, something around that area. And I don't remember the exact number, but after that point, the computer doesn't know, for a computer, for a 64-bit processor that is double precision, which I hope everybody has nowadays. If you still have a 32-bit processor, which is single precision back from like 2004 with Windows XP or something, you need to change your computer. But yeah, I mean, the only equivalent of that will be an Apple product. They're like a MacBook Pro or something like that. Yeah, those computers are shit. But just going back to this, if you have a delta, Beast again here. I've never heard this my entire life. Kasam knows what check is, but do you really think that a guy like him has enough time to go on check and post answers? God, it's like that guy's fucking. He's too busy fishing. He doesn't have time for that. But so this delta value, if I make it too small, I have machine precision. So that's pretty much. I hope that was a good explanation of where machine precision comes from. Is that or approximation becomes too small, that we pretty much, okay, I was looking for something, but I guess I deleted it. Our approximation becomes too small, that to the point that it becomes inaccurate because the computer runs out of memory. It doesn't know how you want to store something. And I don't mean it in the sense, when I say it runs out of memory, I don't mean it in the sense of like, oh, I have an engineering laptop that I'm in depth because of it, and it has 64 gigabytes of like slow as shit RAM, like 2133 megahertz, like he can take it, blah blah blah. No, it's because of the CPU structure. If you have a 64-bit CPU, which all of us have, nobody has a 128. No, Windows cannot support that. Mac can absolutely not support that. And if you have a 64-bit processor, your double precision, it's going to be the same for everyone. And that's what happens with delta in this case. Once we reach to that point in double precision, when our delta value, if we make our delta value smaller than 10 to the negative 17, we're going to achieve machine precision. There's no other way around it. So that's why you have to be extremely careful. Now, this changes depending on the application. And this is where this is relevant. If I'm a heat transfer engineer at Siemens or something like that, and I want to create a fin that has a temperature at the base and it has a bunch of nodes that I want to calculate the temperature of those nodes, and there is the temperature at the tip. I'm gonna call it P, or I should call it T actually, or let me just call it TS for temperature of the surrounding air. Let's say it's an isentropic fin. Fucking shit on Apple, they know. So the number of nodes that we can pack more nodes on a given geometry if we make our delta smaller. So if my delta is smaller, delta represents the distance between each of these nodes. If this delta is small, I can pack more nodes. If this distance is big, the distance between each of the nodes is going to be big. So therefore, I have to pack a smaller number of nodes. So if my distance, and I'm kind of like going, you don't need to know this. I'm just going on a tangent to kind of like give you an idea of what machine precision really represents in the real world, instead of just being, oh yeah, it's the smallest number you can add or subtract from one and still tell a difference. Like, no, there is an actual reason for this. So if I make this distance smaller, I will have a more accurate representation of how the heat transfer is happening on this fin. The problem is at a certain point, this delta has to be, I need to cap it at some point. I need to put it at some point. Like, I need to have a requirement. Like, okay, I want my number of nodes to be 30. I know my dimension is so long. Let me calculate the delta. And then I will go with a number like that. And if the readings that I'm getting, that's where the engineering intuition comes in hand. If the readings that I'm getting don't look quite right, or I could improve them or something like that, I will... There it goes again. Internet connection is unstable. If my approximation is not good, if my approximation is not good, I can improve it by reducing the delta. But one thing that we have to, can you guys hear me, or does it sound all choppy still? I guess we can all watch the video later. Okay. I feel like I just said good for now. Okay, so this, if I can reduce this value to have a better approximation, that's what I want to say. It's a value that nobody, no, it's something that you get out of intuition of just being an engineer and working in the business and understanding a system. Like, if I saw, like, I'm a controls engineer and I do guidance, navigation, and control, and right now I'm currently working on robotics and exosuit. And if I was working on something and I see a value that is not quite right, it's not about controls itself. It's me having an intuition of, like, yeah, like if I'm talking with one of the persons in my group, because I'm the team lead, and then they come at me with some values, and I look at it and I'm like, yeah, this looks like shit. And they might not know why it looks like shit, but me looking at the values, I'm like, yeah, that looks like complete other shit, like garbage. And so I explain why and all of that. So that's why this is something that has to do with engineering intuition. But I want you to understand why machine, yeah, exactly, just like a MacBook. Machine epsilon is a thing, so just keep that in mind. And so another thing that you have to know, and sorry for going in such a big tangent, you have to know about Taylor. So Taylor expansion. Now you might be wondering, do I have to know how to do Taylor expansion? No, the only thing you need to know about Taylor expansion is that when you do Taylor expansion, so the whole idea that we did Taylor expansion is to come up with the definition of the first derivative. If you have a Taylor expansion and you chop it right before the second derivative, you can reorganize everything and get the definition of the forward finite difference, I believe, or the backward finite difference, one of those two. But I think it's the forward finite difference. And the only thing that you need to know from Taylor expansion is when we use Taylor expansion and we chop an infinite process, such as in this case, we are incurring one type of error. And that type of error is, I cannot fucking type today. Truncation. God, that looks horrible. Let me see if I write it again. I feel like my hand's falling asleep. Truncation error. Also, for those curious, I do not have a Microsoft Surface. I'm actually on my desktop. I have a drawing tablet, so that's what I'm using. So I'm looking at the screen while writing on the, like, right on top of the keyboard. I'm not fancy. So yeah, that's all that you need to know. And table cake. The other thing that you need to know is you need to know how to do finite difference. So for finite difference, this is provided. The formula for this, there are three of them. There is forward, there is backward, and there is central. So forward and backward are very similar. These two guys are very, very similar. Central is the only one that really changes. And this is very important that you know, because I don't remember the formula for central off the top of my head right now, but these three formulas, they're provided on your formula sheet. Make sure, for fuck's sake, make sure you print the formula sheet. I don't care if you have to sell your body to get someone to borrow a printer for you, but print the thing, because the lockdown thing is so shitty. and it's so difficult to work with it that just it's easier if you just print it. Just print the formula sheet so you have it. It's a very short formula sheet. Write it down if you have to, but have the formula sheet. Don't try to open it in the middle of the exam, because it opens for some people and it doesn't open for some people, and then we all start getting emails and people start freaking out, and I get messages through like GroupMe, phone calls, everything is like, hey, I cannot access my formula sheet, what's wrong, this and that, and it's like in the middle of the exam. It's like, no, just avoid yourself the trouble, print it, write it down, do whatever you have to do, open a secondary computer if you have to, even though you're not supposed to. Can we down the formula sheet and do it? No, you can write it down. You can write it down. You can write it down, print it, put it on your wall, like whatever you want to do, as long as you have it. Because it doesn't work. I think Kyle made an announcement about this. A lockdown browser doesn't allow you to open it sometimes, because we're using a different version of lockdown browser, and we're from home and this like that. So the whole business of like the addresses and everything, it doesn't let you sometimes, or it opens in blanks. That happened to some people. So just avoid yourself the problem, and tell your friends, family, dog, significant other, everybody who is taking this class, tell them to print the formula sheet. That will be extremely helpful, and you're gonna be saving me a lot of headaches. But finite difference. So the kind of question that you can expect from this is, I can give you something like this. I can say, hey, given delta equal to 0.1, if the value of, like for example, if the value at your current, the evaluation of the function is 2, and the value of the current like position plus the delta is 4, can you approximate that? I'm gonna say like find f prime of that point, and in this case will be like using forward finite difference, and I'm just gonna write it like this. I'm gonna say diff. Okay. And so the way that I'm gonna go about this, if you get a question like this, the way that you go is you say, okay, I know my definition of forward finite difference for evaluated at one point is I have my f x plus delta minus f at that point, and then over my delta. So I'm literally just gonna look at the values. That was from quiz 1. Yeah, so I'm gonna look at the values and be like, oh, what is my f x plus delta? Oh, it's right here. That's 4. And then that's an ugly ass looking 4. So that's 4. And then minus the function evaluated at the point. Oh, that's 2. And then what is my step size? Oh, it's 0.1. And then you're gonna evaluate this, and you're gonna get whatever your solution is. So that's what you need to do on that case. And it's gonna be the same if you're using forward finite difference, if you're using central finite difference, or if you're using backward finite difference. Now I don't remember if they're gonna ask you any conceptual questions with respect to this. Like they should be extremely straightforward, and there are no conceptual questions that I can ask you from this that you should know that you should not know. Like, oh, what will happen if I decrease the step size? Like if I'm using finite, and I just talk about this. If I'm using forward finite difference or no, you don't have to code anything. I said that before I guess I said it in my lab lecture. I'm sorry. I assume that all of you guys are in my lab lecture, so I forget that. But no, class is class, lab is lab. They're separated. You will never have to code anything in class. And the only thing that you have, no, after today, I'm sad that I'm, the only thing that you have to code, it's on the lab. In class and labs are like two different, it's like you're taking two classes at the same time that have a topic in common. So usually during my lab sections, what I do is I share the code. I just go over the code. I explain what each line of the code does. And then I open a thing like this where I draw things that are meaningful to the class. And or I try to explain the concept if you guys don't understand or anything like that. So that's usually what I do. But so for forward finite difference, for any form of finite difference, one thing that they can ask you on the exam is what happens if I reduce delta? What happens if I use a reduced value of delta? And what you need to know is if you reduce the value of delta, you are incurring a form of error, which is runoff. So you are introducing runoff error, because again, the smaller this guy gets, we are increasing the runoff errors, so which is exactly what you saw which is exactly what you saw when you were working on the first assignment. As we kept decreasing and decreasing the delta, we achieve a point of machine epsilon, and then round of error start creeping out. Round of error is everything that is me storing decimal information on the computer, because the computer has a finite amount of memory. The way that the computer worked is you can think of it as a strip of information. By the way, for those of you interested in learning more about computers, there is a YouTube channel called I think it's Computer File, like this or something like that, where they talk a lot about like actual like abstract stuff of computers. It's a very good channel. And I feel like the moment I see a bunch of F's and anyway, I hope you guys can hear me. But Computer File, it's a YouTube channel. It's very good, and it talks a lot about like very good computer information. But the way that the computer stores its memory, it's like you can think of it as a vector. It's like it has a bunch of cells, and what it does, it designates cells for like a specific type of thing. It's like, oh, this is for the sign of the number, this is for like the mantissa, whatever Kasab talks about at the beginning of the semester. I don't remember what it is, but it has an infinite amount of memory. So round of error, if I give it a very long number, sponsor yeah, this is the shameless plug. If you give it a very long number, there is a point where the computer has to be like, okay, no, that's too long, and then it rounds it. It rounds the number before. What happens is after you keep doing more and more floating point operations, which is multiplication, division, and that kind of thing, you will keep rounding and rounding and rounding and rounding, and that's how every numerical app per how can I say implementation, every numerical method like routine will have a form of round of error. There is no numerical method routine that will be perfect, that will have like no error. 10 to the negative 7. That's if you're in single precision. So that's my machine epsilon is, whoa, what's going on here? That's machine epsilon if you're in single precision. What's the largest number a computer can store in double precision? Double precision, it's I set it up there. What is the largest number a computer can store in double precision? It depends. Depends if what you're talking about. I have it right here. Here. So in double precision, it will be 10 to the 308. That's the largest value you can store in a computer. If you Google it, I'm sure it shows you something like this. Or this is in single and this is in double. So, yeah. Like 10, the thing is, it's confusing when it comes to those things of like, oh, 10 to the negative 8, 10 to the negative 7, 10 to the negative 17, or 10 to the negative 16. Those are machine epsilon. It's not the largest number you can store in a computer, but it's the smallest number. It's the smallest number that you can add or subtract from one and still be able to tell a difference. So you're going two completely different directions. You're telling me what is the largest number or the largest value I can store in my computer as the largest number, and 10 to the negative something, or 10 to the negative 7 in single precision, or 10 to the negative 16 or 17 in double precision. We're talking about machine epsilon. Like how small can I go on my delta before my go goes to shit? That's the difference. So you're talking about two different things here when you say 10 to the negative 7 or 5, 10 to the negative 16. You're talking about, this is not the largest. This is like how small can I go in magnitude for, because these are both positive values, but they have so many decimals in front of it. This has to do with machine epsilon or machine precision. That has nothing to do with what is the largest number that I can store. But yeah, moving on, that's what you need to know about forward finite difference. You need to know how to do it. You need to know the conceptual idea of, if I increase the delta value, do I incur the round of error? And then, so the second thing will be, so Newton-Raphson, you need to know that's like everything from like the first part of the exam, and then the next two guys will be, how do you do Newton-Raphson? And how do you do bisection? And sorry that it kind of like I wrote it in the wrong. Sorry that it took too long to get to this point, but I'm gonna try to cover this as quickly. So increasing delta decreases round of increasing. or only decreasing delta. So yeah, in a sense, how can I say this? You're correct with what you're saying. So increasing the delta value will decrease round of error because you are dealing with larger magnitude. So if I have 2 points and the distance is 10, if I increase the distance, if I increase that delta to like 100, I'm still talking in magnitudes. Like the computer is going to be able to store this number properly. It's going to be able to store this number properly, and as I keep getting larger and larger, it's going to be able to keep storing it. It's different when you go into decimals. Like if I go 0.1 to 0.1 to 0.001, like as I keep decreasing my delta, because these numbers, when they get stored in the memory, they're gonna have to be rounded. Like memory is not infinite, particularly in the sense of decimals. Like my computer can store 10,000, 100,000, like all of those numbers, but decimals work in a different way because these two numbers, like if I have 100.00, this goes one place, this goes a second place, and this guy is the problem for round of error. This guy is not. I have memory to store this. Where this guy goes is different. It's a different business because and this is I just want to kind of like do one note. If I want to store something like this keeps going on forever, this guy is finite. I can store it with no problem because I know it's 100. 100 is a finite number. It's exact. I can store it in my memory. Decimals are not exact because remember, everything that you store on a computer has to be converted to binary. So when you think that you are storing 27.3, and I think this is important that you guys all understand it. If I'm storing a number like this, like something like this will convert into an exact binary number. Like it will not be a repeating binary number, it will be an exact binary number. The decimal part will convert into a repeating binary number, like 0, 1, 0, 1, and it will have the bar because it keeps going on forever. This doesn't go on forever, this goes on forever. So that's why those types of error exist, because storing decimals as binary in the computer, they're gonna repeat forever. So we have to truncate them, or when you store certain values on the computer, when you do calculations like multiplication or division of decimal values, those values are often infinite in the decimal part. What about the numbers like 0.5 because of the 2 to the negative is still not valid? Valid things. What about numbers like 0.5 because of the 2? I don't understand that question. What do you mean? But what about numbers like 0.5? The problem is not the number itself. So the problem of how things are stored is not because of the number. It's because of how, if I take 0.235 and I multiply by 0.245, the result of this will be a number that has like larger, like it will have a degree of precision. But what happens is, I can multiply two values that look like this, like assuming that this is all the information that I'm given, but decimal values are not like this in reality. They are infinite. They keep going like a very long time, or whatever you want to call it, a very long size, or they're very large. Even your computer is not exact. Like when you take a number, when you're doing your homework for any class, and you get a solution on your calculator, like it says, oh, the answer is 1.257, blah, 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 blah. Like, and it gets to like up to like 8 decimal places, and then it doesn't show you anything else. It rounded everything else. Like this keeps going on forever, or for a larger magnitude than what it's showing you. Your calculator is kind of like lying to you. It's submitting information from you like a good politician, and there is information that you don't have access to, so that's incurring round of error. That's why when you do mathematical calculations, they say, oh, you should copy paste, or you should use all your decimal values, not just only use the ones that you like. Oh yeah, I'm an engineer, so I only go 4 significant figures, or I'm an engineer and I only go two decimal places. I've seen people like that, and I think that's utter shit. So confirm it, we only need to know yes and no. So I believe there is one question on the exam that asks you, hey, repeat the same thing you did with Newton-Raphson, but use Secant method. But what I want you to understand before anything, before getting into like bits and pieces of every method, one thing that it holds true for all of them, it's the way that we calculate residual, iterative convergence, and I think there are certain things that are specific, and I also want to talk about speed of convergence before I talk about how to do each of these methods itself. So if you have any questions, because I don't know if I'm gonna have enough time to like work an example or anything like that. I want to make sure that you guys understand what's on the exam and how to tackle this type of problems. But the best way that you can handle one of these problems by yourself, or you can attempt one of these problems by yourself, go into YouTube, go into Numerical Methods Guy. He has examples of how to do Newton-Raphson and bisection, and that's what you can expect from the exam. Like as far as how do I solve this problem. But I want to make sure that you understand what maybe he doesn't cover in those videos, and the type of questions that you're going to expect. So for Newton-Raphson, bisection, and secant method, there is something called the residual. So I am going to draw a graph right here, and this is my x, this is my y for my f of x. I have my function right here. This one is going to be my f of x function, and I'm going to approximate my first root to be this one. This one is going to be my initial guess. That's my initial guess. That's what we're going to give you guys. And that initial guess, if I plug in the value on the function, it evaluates to a value of that function at a certain point. Now, let's say let's say I'm doing Newton-Raphson or I'm doing bisection. Regardless of what I'm doing, I use that initial guess. I do whatever method I needed to do. For Newton-Raphson, I found the new root. Give me 1 second. For Newton-Raphson, I found my first. I should use the correct notation, because once we get into vectors, it's gonna be confusing. So I use my initial guess to find my new one. This is fx divided by f prime. So I use this to find my new approximation of the new root, or if I'm talking about bisection, what I did was the new root. I think we use c, but I'm gonna use x1 just to kind of like follow. So my first approximation of the root was b plus a, or a plus b divided by 2, where a and b are my brackets, and this gave me my first approximation of the root. It might not be the exact one for both of them. There's supposed to be a question on secant too. Yeah, there's a question on secant, and that guy landed me here. So again, I'm closer to the root. If I evaluate that function, I have x1. So what I want to talk about is the idea of residual and iterative convergence. So residual, which is given as an r, it's equal to the absolute value of the function evaluated at a particular iteration. So I'm gonna put n in here. It's at a particular iteration. It's the absolute value of the function. Now, what is this in a graphical idea, or in a graphical aspect? Residual is the distance. In this case, this is the initial residual. If they ask you for initial residual, is the distance on the y-axis of how far, what is the magnitude? That's why it's an absolute value. Is the magnitude of the distance from the evaluation of that root to the x-axis. Because remember, what are we trying to, when we do solution methods, when we do Newton-Raphson or bisection, what we want to achieve is we want to go, hey, find the x value that if I plug that x value into my function, I get a 0. If and only if f is equal to 0, what this tells me is that x is a root. This is basic algebra. X is a root of my function. If when I plug it into 0, when I plug it into my function, I get a 0, which is exactly what I want. So what the idea of residual is an indication. It's a way for me to know if I'm approaching the x-axis, because as my residual, that's my initial residual, then this is my residual at the first iteration. As I keep finding new solutions for the x, and maybe the next one is going to be here, then the next one's going to be here, and then here, and then here. As I keep finding new iterations of my approximated solution, what do I expect to happen to my residual? My residual is going to go down. It's going to go to 0. Why? Because any function, if I'm at a root and the x value happens to be my root, if I plug that into my function, I should get a 0. If x is a root of my system and I plug that x in my function, I should get a 0. Using that same definition, if I take this f and I evaluate it at an x that happens to be my root, and I take the absolute value of that, my residual should be a 0. This is why we use residual as an stopping parameter for the code. We use one of the two that we use. The other one is the iterative convergence. The first one is the residual. So if you want to know what the residual is the distance of the evaluation of the function at that current x. It's something that as we keep iterating should go to 0, because as we approach the root, as we approach the x-axis, at the x-axis y, or the function, or the value of the function, is 0. That's why it's the x-axis. So as we approach that point, I see this y value, or I see this f of x value going to 0. That's why my residual goes to 0. Now the next thing to talk about is what is known the iterative convergence. So epsilon, which is, I'm gonna close the chat for a second. So the epsilon, which is the iterative convergence, and I'm not writing in the same color. So epsilon is the iterative convergence, and the iterative convergence is actually the absolute value, again, because we care about magnitude. We don't care if something is positive or negative. I just care about the magnitude of something. I have my x at whatever iteration minus my x at a certain iteration, and what happens is this is my xn plus 1, this is my x1. So if I wanted to find something like my iterative, like this one, I want to find what is my epsilon 1. So my iterative convergence after one iteration, I'm gonna have the distance for x1 minus my initial guess x0. This right here tells me how far apart one of my x's is from the other one. So every time I compute a new solution of my x, every time I find the new x1 or a new iteration, be it whatever method I use, every time I find a new one, I have to calculate the residual, and I have to calculate the iterative convergence. Why? Because as I keep finding more and more solutions, like, hey, let's assume this is x2, and this one over here is x3, and then x4, and then x5. As I keep approaching, as I keep iterating and approaching this solution, this root that is the exact solution, the solution that I'm trying to find, the iterative convergence, the distance between my new x and my previous x, has to go smaller. So this guy also, sorry, I wrote the wrong thing. This guy also has to go to 0, because the distance, as I find new solutions, like this is x1, x2, then x3, and x4, x5, x6, x7, as I get close to the real, to x real, like the real solution, the distance between my new x and my previous x should go to 0. In the same manner, as I am approaching the solution, that x root, the distance of my y-axis, the magnitude, because just because of the behavior of a function, as I approach that root, the evaluation of the function, or the magnitude of the evaluation of the function, should also go to 0. So these two ideas, residual and epsilon, these are the same formulas for all of those three methods, be it Newton-Raphson, be it bisection, or be it secant method. If I want to find the residual, I take whatever n at whatever x at whatever iteration I'm working on. Keywords that know and to keep in mind is, if I ask you for the initial residual, the x that we will use here will be the x0, will be the initial guess that you're provided. So if we ask you for, hey, find the initial residual, you're taking your x initial guess, you're plugging it into the function, not the first derivative, the function. There's no reason to plug something into a first derivative. You plug it into the first derivative, you take the absolute value of that will be your initial residual. If I want the residual after two iterations, you will take the x that you obtain, being by the bisection method or the Newton-Raphson method, after two iterations, you will plug it into the function and take the absolute value of that. Iterative convergence, it's slightly different in the sense of you have to have at least one iteration accomplished. There is no such thing as an initial iterative convergence. In the code, we often define it as like 10 or 0 or whatever number, and I went over this in my lab lecture of how why we just assign whatever random value or 0. Because if it's your initial guess, you don't have anything before that. So what difference am I gonna find? If I only have an initial guess and I haven't even done one iteration, this will be like x0 minus x minus 1. That doesn't even exist. I don't have minus 1 iteration. So you need to have at least one iteration. So if you accomplish one iteration either by the Newton-Raphson or Bisection method or even Secant method, and I ask you to find the iterative convergence after one iteration, that will be your x1 minus your x0. So your solution after one iteration minus your solution at the initial guess. Now, this is not always the case. If I ask you for the epsilon or the iterative convergence at the second iteration, it will be x2 minus x1. So it will be your second approximated solution minus your first approximated solution. So you always, every iterative iteration or every iterative convergence calculation uses the value that you just found. Like if I did 4 iterations, I'm gonna use the approximated solution that I just found minus the previous one. I don't use anything else. It's always the one that I currently found minus the previous one and absolute value of that. So if I asked you to find me the iterative convergence after 4 iterations, it will be the absolute value of x4 minus x3. And that holds true for everything. That holds true for Secant method, for Newton-Raphson, and for bisection, because these are definition of root seeking for linear for single variable functions. Let's put it that way. I think I have one comment in the chat. So initial convergence is always 0. It's always 0 for it. It doesn't matter. It can be anything. It's for coding. For coding, we need to have because in coding we have to define arrays. You cannot define an array as invisible, or as you can define it as a nan, but it makes no sense from a mathematical perspective. So we usually set it to 0. You can set it to whatever you want, because conceptually it doesn't make sense. Your initial such thing as an initial convergence doesn't exist because you only have one point. You don't have anything to do the subtraction or find a reference. So that's why we include it in the coding. You will never see it in an exam or in a quiz or anything like that. They're not gonna ask you what is the initial convergence, because what are you subtracting it with? You're not If your initial guess is the only solution that you know and you don't know anything else, there doesn't exist anything else. So if the question was find the third iteration, yeah, exactly. So you will use the x from your third iteration minus the x from your second iteration. It's always whatever they ask you, that's the current iteration that you're gonna use. So if I ask you iterative convergence at the fourth iteration, it will be absolute value of x4 minus x3. If I ask you for your residual at the fourth iteration, it will be take the x4 that you found, plug it into the function, take the absolute value of the result, and that holds true for all of them. So that I think that should clarify those ideas. And there is I can talk a little bit. I have some time left, so I can talk about bisection and Newton-Raphson. So Newton-Raphson and bisection, it's all pretty straightforward. For Newton-Raphson, you just need to know this formula, which I showed before, and I hope that I still remember it correctly, because I haven't even opened the book or look at anything. So your xn plus 1 is gonna be equal to your xn minus the function with that x evaluated at the current point divided by the first derivative of at that x. Now, one thing that is important to note from Newton-Raphson is Newton-Raphson requires the evaluation of the derivative. So if they give you a function, if they give you a conceptual equation like, hey, what do we need for Newton-Raphson, or how is Newton-Raphson different than bisection, or something like that, Newton-Raphson requires two things. It requires an initial guess, which you're going to be provided, and it requires a function, which you're going to be provided, and it requires a first derivative. So you have to, why don't we use secant all the time if it's the best? Secant method is not the best. The secant method is Newton-Raphson, but without requiring the evaluation of the first derivative. So Newton-Raphson actually used the idea of finite difference of using the rise over run, like it uses the idea of the slope to calculate this guy. So imagine if I instead of finding the first derivative, like if that's the first derivative and I say, hey, you know what I want you to do? I want you to take the evaluation of x plus delta minus fx delta, and I want you to plug it in here. Like that's pretty much what we're doing. So we're approximating this f prime, which Newton-Raphson, if you know the first derivative, if you know the first derivative of this, it will be, you're not putting as much error, because if you approximate your f, if you have to approximate it to use it, then you're going to be putting some error into the system. However, it all depends. All of these methods, there is no method that is better than another method. There is no. It all depends on the scenario that you're working with it. Newton-Raphson, it's extremely. Oh, I have to talk about the speed of convergence. Don't let me forget. But Newton-Raphson, it's some. If you have something like this, if you have a repeating root for something like a tangent or a cotangent, something that goes like this, like you have something like this. That's your function, and all of these guys are asymptotes. So these are asymptotes. Because I don't know if you remember from trig, but this is kind of like the graph of tangent or cotangent. I cannot remember which one it is. So if my root it's somewhere in here, and I have another root here, and I have another root here, if I were to implement something like Newton-Raphson, which if you go into Wikipedia, you can see the animation of how it works. It will go crazy. It will not be able to converge to a solution because Newton-Raphson sucks with trigonometric function, especially those who have asymptotes, because it's not just the base way of doing it. However, if I use something like bisection, what it does is I create a bracket. I have a good idea of where the bracket is, so I'm gonna, or where the, whoa, what is that? I have a good idea of where my root is, so I can define my A and B bracket, and then I can do the bisection, which is, it's kind of like a segmentation to find that solution. So bisection will work best on a scenario like this, because of how I have asymptotes and I have discontinuities and all of that. Whereas Newton-Raphson will pretty much have a stroke trying to find a function like this. But if it's a well-defined smooth function, something like this, then Newton-Raphson will be the method that I will use instead of bisection because of a speed of convergence, which that's a point that I want to talk about. Let me just read the comment real quick, or the chat before I talk about that. That was ink to shave. Yeah, I noticed. It was very unexpected. So how can I tell if it? Why don't we use secant all the time? How can I tell the Newton-Raphson will converge on diverse? There's no real good way of knowing. If you can have an ill initial guess or you can have a good initial guess, you can tell if an iterative method. There's something I forgot what it is. And this might be a question that appears on the exam. I believe there is another method that you guys saw for solution seeking. I don't remember what it's called. It's iterative something. It's a method of iteration, but it's not Newton-Raphson, it's not anything where you have a function f of x, something like this. So let me give you an example. Let's say we have this x squared plus 3x plus 5, and I want to find. Let me just read it. So just like for iteration, will the third residual be? No, the function, yeah, there you go. So the residual, this is the formula for iterative convergence. Iterative convergence is the only one that has a difference. Residual is you take the function, you take the solution that you found, you plug it into the function, and take the absolute value. Yeah, that's what it's called. So fixed point. So if you want to do fixed point iteration, if you're doing fixed point iteration, what you do is you take that, you set it equal to 0. So you have x squared plus 3x plus 5 equal to 0, and you solve for your x. So x, it's equal to the square root. That's a big ass square root. You take the square root of -5 minus 3x. And what you do is you're gonna call that your function g of x. So this is a function that you will be using to iterate. I believe there is a question on the exam like that it gives you a function like this and it tells you, oh, what will be the form of iterating. So you set it equal to 0 and you solve for x. You move everything to one side and you create that a new one. However, there is a thing here that you can guarantee convergence, and I believe it's in the formula sheet. I think it's the last equation on the formula sheet. If you're using fixed point, so for fixed point, you can guarantee convergence if your x prime it's less I believe it's less or equal than 1 for all x's that belong to like the real numbers or something like that. So it's like what this is trying to say is just all x in real. So all the x's, if I go 0.1, 0.2, 0.3, 0.4, whatever value I put on my first derivative, if the evaluation of my first derivative is smaller than 1, I don't remember if it's less or equal. It's on the formula sheet, but you can guarantee convergence of fixed point iteration by doing this formula. By the prime of evaluated at any x has to be less or equal than 1. I think it's just less, but I'm gonna go with x or equal just to play safe. And then for all x's that belong to the real domain. But yeah, that's what you need to know for that. It's just less. Okay, so
Wait, so you rearrange the equation, you get x equals square root of -5 minus 3x, and then where do you go from there? And
that's it.
do you,
That
like, plug in
that
root?
is your equation. So that equation, that x, we can actually call it like g of x. And then from there you
Okay,
just
so then and then would you use a different like iterative method then to solve it
so
or
fixed
something?
fixed point iteration is its own iterative method. I don't really remember how you do it. Like if you plug different values of x in here and then you get to a particular solution. I don't remember. Like I think I'm trying to remember. I don't remember what you do from here, to be honest with you, because fixed point iteration is not very useful. But I think this is all that it asks you on the exam, just to put it in this form. Like this is the fixed point iteration form. Yeah, and
Oh, perfect. Okay.
huh? I don't really remember if we have to find if there any kind of go to the last page formula set. Yeah, I cannot remember if there is any what is the way of solving this, but I don't think it's asked on the exam. I can always be positive that is not asked on the exam. Now before, because I only have like 15 minutes left, I want to talk about speed of convergence. So speed of convergence, and this is something that you can derive. However, I'm not gonna go through the derivation. I'm just gonna tell you what the values are. So you have bisection. So bisection method, the k value, which is the convergence value, it's k is equal to 1, and this means that the speed of convergence of bisection is linear. And that's bisection method, k equals 1. And secant method, so secant method, the speed of convergence is approximately 1.7. I know it's like 1.6 is something, but I'm just gonna go with 1.7. And this is what is called a superlinear. And Newton-Raphson, which is the last one. I don't think Newton has an H. I think it's just like this. Newton-Raphson. The speed of convergence is 2, which, as you might be guessing, this means is speed of convergence is quadratic. So for bisection method, the speed of convergence is 1, which makes it linear. The second method, secant method, the k is equal to 1.7 approximately, so it's super linear. And Newton-Raphson, the speed of convergence, k is equal to 2, which it makes it quadratic. We don't explore any method or anything like that as far as of now that has to do with exponential convergence or anything like that. Quadratic and linear are double root for. Are you saying that linear is quadratic at a double root?
Now, what I'm saying is the speed is linear if you have a double root. That was a question on the quiz, and I got wrong, and then Kasab explained it to me.
So if it's a double root, which one changes?
The Newton-Raphson
It becomes linear.
becomes linear. Yeah.
Okay. All right. Perfect. Thank you.
Yeah, just for a double root. Yeah, just that's an add-on for everybody.
Okay, that's perfect. I don't think they're gonna ask you that on the exam, but it's good that you know it.
Yeah, it's very specific question.
Yeah, perfect. Thank you. Thank you for adding that. And I think the only thing that we have left that we're missing here is so this is specific for bisection. In bisection, for bisection method, there is a formula, and I don't have the formula sheet with me, but they will ask you something like, what n number of iterations. So one n number of iterations are needed if they give you a certain tolerance, like if they give you a certain epsilon. So if they give you something like, oh, if epsilon is 10 to the -6, I don't remember how the formula is. It's like it's n is equal to like ln of something, ln of like b minus a divided by something. I don't remember if it's something like that. It's under your formula sheet, and I can Google it real quick. But what you're gonna do is you're gonna take that epsilon value, and you're gonna plug it wherever you see an epsilon, and then your b and your a are your brackets every time. So bisection, going a little off tangent here, bisection requires to have an a b, and the function. So this is different than Newton-Raphson, and this is why bisection is also better at certain aspects of root finding, because a and b your a and your b are just brackets, they're values. So we require two initial guesses. So for bisection, you require two initial guesses, which is your a and your b, but you do not require the evaluation of the first derivative. So if you have a very complicated function or a very complicated system that you're trying to work on, your a and your b, your going about it is gonna be easier. It's gonna be slower because of speed of convergence, but it's gonna be easier when dealing with very complicated trigonometric function of multiplication of like e to the something and natural logs and all of that, because of the fact that we don't require to find the first derivative or approximate the first derivative. But there is an equation like this, and I can probably Google it, but 'cause I don't want to Google it and then I give you like something that is not as an example of this given tolerance. Okay, that's perfect. So slide 49 in lecture 3, Matthew is saying that he has an example of this given the tolerance. You have it upside down. Go figure. I knew it was something similar. So just flip this. I haven't seen this in forever, but I have like vague memories of this. But yeah, so they will give you the epsilon, and whatever n value you get, that's your number of iterations. One thing that I do want to say about this is if your n gives you something like 8.7, you have to say that it's 9. So you round it up, and it's ln2 instead of lne. Oh, okay. So it's ln2. I knew there was a 2 somewhere, because the something was like to a power or something like that. But if you go into Wikipedia, you can see this equation in the non-derived form, but in the formula sheet, they're giving it to you in the derived form. So just use what you're given. When do you round? So if you get a value like 8.7, you cannot have 0.7 of an iteration. That's like saying like, oh yeah, we need 2.5 people. Like you're not chopping someone in half. So you have to round up. You have to go to 3 or something like that. Or in this case, I go to 9, just to be safe. I don't believe we have to round down. I am almost positive we round up.
So if you get like 8.1, you round that up to 9.
I will say so because the way that I look at it, or the way that I think about it, is if you know that to achieve that certain tolerance, you need more than 8. So if you get 8.1, you know by a fact that you need more than 8. So if you round down, you're not achieving that tolerance by any means. So the only way to go about something is rounding up. If you do this on the exam and you get it wrong, I will give you points back, because it makes no sense. So that's why I'm kind of like getting it out there. So on the formula sheet, has the yellow on the border to reach the error tolerance. Yeah, somebody said that before, I believe. I have, that's why I have this thing, meaning flip it. Yeah, epsilon is your tolerance. So in numerical methods, numerical methods, and something that you saw on your code is every time we refer to the word tolerance or tolerances, like if we say tolerance, we're talking about two things. We're talking about epsilon and we're talking about residual. So that's why these two guys are stopping parameters when we are dealing with the code. That's why there is an if statement with a break and everything inside of every single function that we work on that says if we reach this tolerance or if we reach this residual, or if it's a good code, if we reach this and this, you can break the code, because at that point we have achieved a certain tolerance. Therefore, we can stop the code and we can report our solution for the X as accurate. We can report that solution as accurate, because if we never set these tolerances, the code will keep on going and going and going forever. All of this method, Secant Method, Newton-Raphson, and Bisection, they go forever. There's nothing to stop them. The computer doesn't know what is a good solution. It will just keep going on and on and on and on forever. And at one point, if you look at your project and assuming you did a good project and everything, or your TA went over it, you will notice that as residual goes to 0 and iterative convergence goes to 0, your X solution starts kind of like converging towards a value. Like if the real value for a mass is 2 kilograms or 2 grams or something like that, your solution will start like at the initial guess, which is maybe like 5, and then we'll go 2.1. 2.9, 2.5, 2.2, 2.1, and then it will like start oscillating around so if the real solution is 2, it will go like 1.95, 1.955, 1 point something something, 1.99, 1 point, and until it gets to 2. So it will get extremely close to the solution, and it only knows when to stop depending on your tolerances that you set up. But I think that's everything for the exam. That's all that I wrote down that I saw on the exam, and I think it's important to go over. So I will finish recording. Hopefully the recording did not crap out, because I know last time I did a review section during office hours. My microphone did not work for whatever reason. It was working on the Zoom thing, but it was not working on my recording. I have an AMD graphics card, so I was just using that. But yeah, child play. I'm just using the built-in thing from the Radeon software. What else? I think that's everything. So I will upload this on YouTube. It should be a pretty small file. I'm using HPC5 or whatever it's called. And yeah. So for those of you who were not able to see it or just want to go over it or something like that, let me know and I'll send you the link of the video. And I'm gonna have it unpublished, so it will not be out there. So we just look up your name on YouTube. The problem with looking up my name on YouTube is upload to OnlyFans. I need my OnlyFans account. I'm actually, maybe I should create a Patreon or something. No, so my name, send me a message on Web Courses and I'll send you the link once it's uploaded. I'm not gonna publish it. I'm gonna have it as unlisted, because I don't want to publish it and then Dr. Casa gets angry at me because of giving information about the exam or something like that. So because this is a review and because all recorded, I'm just gonna keep it as unpublished. And yeah. But once you find the channel, I have other videos in there for, I think, Project 5, 6, and 7 or something like that. So you're more than welcome to go over those as well.
Thank you.
Yeah, you're welcome. I will share the link to one of you, and if you want to share it or group me, that's up to you. That's not, I cannot go and publish it myself. So somebody has to do it for me. So send me a message, I'll send you the link, and then you can do whatever you want with that link. But yeah. That's perfect. All right. Thank you, guys. Thank you for joining. Hope it was helpful and muy amable. Hope you do good on the exam. If you have any questions, I'm going to try to answer emails as much as I can. So, yeah. All right. Thank you. Feel free to stick around if you have any specific question, but I'll stop the recording now. Let's see.